Well, let me remind you what methods we have other than just direct integration if the right side is a function of t for solving a differential equation. We have separation of variables. We have the method for linear equations for solving first order differential equations. And that's it, really, other than direct integration. In the lucky case, the right side depends only on t. Here's some other methods, and a lot of the other methods actually tend to be just clever substitution methods to reduce to one of those other methods, separation of variables or a linear equation. Right? So here's one of them. Suppose I have a differential equation that looks like this. dy dt is a function of y over t only. Whenever t occurs, it occurs as, or y occurs, it occurs as the quotient y over t. Then this substitution, let v equals y over t, that looks obvious, right? If f is a function of y over t only, then why not substitute v equals y over t? Natural thing to do. If you do, then you can make this calculation. I should write it out here. If you make the substitution v equals y over t, then it follows that y equals v times t, and dy dt then must be equal to, by the product rule, dv dt times t plus v times 1. So it's v plus t dv dt. So when you make the substitution v equals y over t, you also substitute for dy dt v plus t dv dt. Let's bring that back. Here it is. Substitute v equals y over t and dy dt equals v plus t dv dt. And what turns out to happen is any equation of this form is transformed into a homogeneous equation by that substitution. Then you can solve it into a separable equation by this method. And then you can solve it by your separable equations method. This is called a homogeneous equation. It's different than a linear homogeneous equation. This means that function f is a function that's homogeneous of first degree in its argument. So it's a different kind of homogeneous. I'm sorry, homogeneous at degree 0, actually. All right. Now, solving for, in some equations, if you if instead of writing dy dt, if you have an equation of this form, I'm sorry, this looks terrible, doesn't it? We don't have any method for that. But if you take the reciprocal of each side, right, dt dy equals a of yt plus b of y, recognize that's a linear equation for t as a function of y. So you can solve for t as a function of y instead of y as a function of t if you just take the reciprocal of each side. So that's another kind of equation. You can sometimes get a linear equation by taking the reciprocal of the given equation. This is another one. I think I'm going to omit this one for now. We might do this later. But I'll give you some homework on some of these other ones. A special case of that is the Bernoulli equation. If an equation looks like this is almost linear, right? dy dt plus p of ty equals f of t without this y to the n is a linear equation. We already know how to solve those. Oh, what if there's a y to the n multiplying that? That seems like an unlikely thing. Actually, that happens to come up a bunch in fluid mechanics, and one of the Bernoulli family then had to solve this problem a lot for fluid mechanics. And so we found out that this substitution, let v equal y to the 1 minus n, turns an equation like this, now called a Bernoulli equation, into a linear equation. So here's an equation of this form where it looks linear except there's a y to the n multiplying at the end. Can be made linear by substitution v equals y to the 1 minus n, and then you have to replace dy dt also. We'll do that in the example. And here's an equation where you substitute v equals y over t to make it into a separable equation. So convert it into one of the kinds we know. Then there's a Riccati equation. I'm going to skip that one this semester, I think. If we have a little time at the end, I might get back to it. Those are of occasional use, not as much as these others. So let's look at these two that we did. And we should look at the third one. Let's look at the other one now. if you have an equation of this form, dy dt times g prime of y plus p of t, g of y equals f of t. These come up once in a great while. What's once in a great while? Well, Bernoulli equations actually turn out to be a special case of these. Bernoulli equation satisfies this. So any equation like this, a little more general than Bernoulli equation, but not all kind of common, can be made linear by a substitution v equals g of y. If you do that, this just becomes a product rule over here, and you can integrate it. So, and that's what happens. We'll do an example here. So here's the first one. Theorem, we just already derived this part. Substitution of v equals y over t and dy dt equals v plus t dv dt converts a homogeneous equation, an equation dy dt equals a function of y over t only, into a separable one. Here's the proof. Substitute v equals y over t, in which case y equals vt, and you get this derivative that we derived. Putting these into the homogeneous equation, which was dy dt equals f of y over t. dy dt gets replaced with this, and y over t gets replaced with this, v, right? So you just replace, it was dy dt equals f of y over t. So we replace y over t with v, you replace dy dt with v plus t dv dt. And now, once it's in this form, you can subtract v over and divide by t, and you get this. And that's separable, right? Because it's a function, it's dv dt equals a function of v times a function of t. It's a product of, that you can separate the variables to each side on. Alright, so how can you recognize a homogeneous differential equation? One way to recognize it is, often it's given in that form, but if it's not given in that form, you can try this. Replace t with t tau and y with y tau, and if f of t tau y tau is equal to f of ty without the tau, then it's homogeneous, because what you can do is once you, if these two are equal, f of ty equals f of tau t tau y, then you can replace tau with 1 over t and get f of 1 y over t, showing that the function can be written as a function of y over t only. Right? If f of t y is actually equal to this, then replace tau with 1 over t, and it becomes f of 1 y over t is a function of y over t only, not just t or y. So that's the proof. If this is true, then the function is homogeneous. So here's a function, you can tell it without using that trick. dy dt equals y squared over t squared plus y squared plus y over t. How do I know that's homogeneous? Well, if you think about it, divide top and bottom by t squared, and this becomes y squared over t squared over 1 plus y squared over t squared. And you can see right away everything is just a function of y over t. But if in doubt, just try it. F of tau t yt is tau squared y squared t squared tau squared y squared tau y tau t. And now the tau squareds on the top cancel the tau squareds on the bottom, the tau on the top and the tau on the bottom. Give f of cancel the taus and give you f of ty back. Since these two are equal, we know it's homogeneous. So we rewrite it by doing what I saw instantly, replacing, just dividing top and bottom here by t squared to get this, and leave this one alone because it's already y over t. And then y over t is v, y over t is v, y over t is v, and dy dt gets replaced with v plus t dv dt. So a homogeneous equation, replace dy dt with v plus t dv dt, replace each y over t with v, and now this is separable. Look, I'll subtract v on each side and I'll get, oh boy, I did two steps at once, maybe it's hard to see. Subtract v from each side, you got t dv dt equals this, and then you can multiply by dt over t and get this equation. And you separated variables, d's with dv and t with dt. It's a separable equation we got. We proved up above that you always get a separable equation, right? So now we just have to integrate this and integrate this, and we, sure enough we can. Integral 1 over v squared is minus 1 over v, integral 1 is v, integral 1 over t is ln absolute value of t, and there's an arbitrary constant that floats around. this gives you this equation. Unfortunately, when you separate variables, remember you get an equation that implicitly describes solutions. You have to figure out pieces of these along which v is a differentiable function of t. In other words, you have to solve for v as a function of t out of this. Well, fortunately, alright, it's like a quadratic equation. ab squared plus bv plus c equals 0. You can solve for v with the quadratic formula. Right? V equals minus the coefficient of b minus b plus or minus square root b squared minus 4acl over 2a. The quadratic formula is using a, b, and c. These functions of t in general. And here are two solutions, right? This is actually not a solution by itself. It implicitly determines these solutions. One solution for the plus, one solution for the minus for each value of c. So there's an infinite number of solutions given in pairs here. Alright, so now we can say, furthermore, v is y over t. So if we write that as y over t and then multiply both sides by t, we get this. That y is actually t over 2 times ln t plus c plus or minus square root. That's writing solutions y as a function of t. Well, I want to point out that these homogeneous equations have important applications. These kind of differential equations come up in certain mathematical models in biology and chemistry, I think. dy dt equals a linear function, ay plus bt over cy plus dt, and more generally these kind of equations. And you can make substitutions that make these equations into homogeneous equations that you can solve by this method always. So see, homogeneous isn't all that rare. These things with linear numerators and denominators always convert to those. Is one interesting case. Suppose I want this case. dy dt equals y minus t over y plus t. Well, if I divide top and bottom by t, I see that's y over t minus 1 over y over t plus 1. Oh, it's a function of y over t only. It's homogeneous, right? So see how these equations convert a lot of times. Take a look at the notes. I gave detailed notes with these examples. These are the notes. Substitution of v equals y over t and dy dt equals v plus t dt on the left gives us, right, v plus t dt equals v minus 1 over v plus 1. This is always separable, right? This method always works to separate variables. So you subtract v over here, and then you do some algebra on the right-hand side after subtracting an algebra. It gives you v squared plus 1 over v plus 1 on the right equals what's left on the left, t dv dt. And now multiply by dt over t, and the reciprocal of this to separate variables, right? Multiply by the reciprocal of this one, reciprocal of t and dt. To get this equation where the variables are separated and you integrate both sides, this one's kind of a tricky one. You break it up into two pieces, right? If you integrate v over v squared plus 1, you can do that with a u substitution, right? Substitute u equal v squared plus 1, and then du is 2v dv, so you get 1 half 1 over v squared, 1 half 1 over u du. Anyway, you can make a substitution u equals v squared plus 1 and find that this integrates to this v over v squared plus 1 gives you 1 half ln v squared plus 1, and then integrate 1 over v squared plus 1 separately. Remember that one by memorization is the arctangent of v. And then integral 1 over t is ln absolute value of t, and there's an arbitrary constant for the integrations. So here's what you get for implicit solutions. Then you can try and solve this for v as a function of y. Sometimes this one is not so easy. We'll just put back v equals y over t, right? How can you solve for y out of that? It's not so easy when it's inside the logarithm and the arctangent. So we'll just say solutions are implicitly defined by these curves with c arbitrary, and you can use the computer to go plot a bunch of points on these curves and get pretty accurate positions and see what the solutions look like, even if you can't write y explicitly as a function of t. Well, here's another equation that we were interested in. This kind, dy dt equals 1 over a function of y times t plus a function of y. We recognize immediately if you turn it over, it becomes dt dy equals minus a of yt equals b of y. This is a linear equation for t as a function of y by our very definition of linear equation, right? And so here's an equation like this. Suppose I give you this one on the test. 2 times t plus y squared dy dt minus y equals 0. I could put it in the normal form, right? If I see a nonlinear equation like this, right, it's y to the sixth, it's certainly nonlinear. So let's put it in the normal form and so we can apply the existence uniqueness theorem, and it looks like this. dy dt equals y over 2 times t plus y to the sixth. It doesn't look separable, right? I can't multiply and get all the y's on one side and the t's on the other. It's certainly not linear, it's y to the sixth. How am I going to solve this? Well, all I got to do is the upside down, right? The dt dy equals this upside down gives this equation. And now I pull the 2t over y over here. And I notice now this is dt dy plus a function of y times t equals a function of y. This is actually a linear equation for t is a function of y. Right? This is like dy dt plus p of ty equals f of t, except with t and y interchanged. Alright, that's what I'm pointing out here. We can solve any linear equation by an integrating factor, or we can go straight to the formula. The integrating factor is e to the integral p of y dy. I'll call this dt dy plus p of yt equals f of y. And it's just the linear equation form with t and y interchanged. So the integrating factor is 1 over y squared. I can multiply through by the integrating factor and integrate this, or I can go straight to the formula. This is the formula. 1 over mu is y squared, integral of mu p f of y dy. Remember, this is the formula for a linear equation. 1 over mu, integral mu f of y dy instead of f of t dt when t was the independent variable. And so you do this integral and you come out with t as a function of y. Not completely satisfactory because really the solution is y as a function of t. But boy, that's hard to solve for t. This is maybe the best you can do. Again, you can plot points on it and you can say, well, I solved for t as a function of y. That can be a great benefit too. Now, if we have an initial condition also that y of 1/2 equals 1, then we can plug it into here. We plug in 1/2 for t and 1 for y, and we get 1 here, 1/2 plus c times 1 equals 1/2. And that shows, if you solve for c algebraically, you get c equals 0. And so actually, t equals 1/2 y to the sixth is the unique solution for our initial value problem. And I also apply the initial value. And this one is easy to solve for y, right? It's just y equals 6th root of t is the unique solution of the initial value problem. So we were able to solve it for this particular initial value. All right, well, pretty tough, huh? Here's this one. The substitution methods, though, just think of them as, here we have 4 substitution methods. I'll omit the Riccati equations, which I deleted from actually the notes down here. We want homogeneous equations. We want these linear by taking the reciprocal equations. We want this substitution method. If we say dy dt times g prime plus p of t times g of y equals f of t, we see something like that. The substitutions let v equals g of y. If we do, then if v is g of y, then dv dt is dv dy dt, which is g prime of y dy dt. Oh, that's just what we have here. So this is really dv dt, and this is p of t times v, and we can rewrite this as a differential equation we can solve. So let's try this one. Suppose I want to solve the 1 over y dy dt plus ln y equals 2t. What a hard one. All our other methods fail. But we notice that this is of this form, right? dy dt times g prime of y, where g of y is ln of y, all times a function of t alone 1, equals f of t 2t. So if you think of p of t as 1, then this is of this form, so I just want to substitute v equals whatever function of y is here. Ln y is what that suggests. Substitute V equals G equals ln y in this equation. If I do that, then I also need dv dt as its derivative with respect to t. Is derivative ln y with respect to t is the ln y dy dt by the chain rule is 1 over y dy dt. I told you this course will make you very good at taking derivatives because we really got to use them theoretically. And now you see why you don't just want to use symbol lab to do all your derivatives in calculus. This theoretical stuff will kill you in this course if that's all you did was learn symbol lab, right? You got to be able to do these complicated theoretical calculations. dy dt, the ln y dy dt is 1 over y dy dt will be dv dt. So I take the 1 over y dy dt, that becomes dv dt, and then ln y is v equals 2t, and now look what I've got. This converts into a linear equation. That's the point of the substitution. An equation of this form, substituting v equals g of y, converts it into a linear equation. Now, from the linear equation, I know how to solve by formula. Mu be e to the integral of 1 dt, whatever multiplies v here, right? That's why we did linear equations before this. It's e to the integral of 1 is e to the t. And then the formula says 1 over mu is e to the minus t times the integral of mu e to the t times f of t to the right-hand side dt. So by the formula for linear equations, we see the solution is this, which is e to the minus t times all this stuff. There we have it. The solution, the set of all solutions to this equation by integration. Looks like 2t minus 2 plus c e to the minus t. How about that? From which you can write, since v is y over t, write this as y over t multiplied by t. Oops. Oh, I'm sorry. V is not y over t. V is ln y. See, if this is ln y equals that, you take the exponential of both sides and get y equals e to all this stuff. There we go. So there's the solution. You have to write y as a function of t. And then finally, a special case was said the Bernoulli equation. If you see something like this, it looks linear, but it's got a y to the end at the end. Then you can substitute v equals y to the 1 minus n. Now, implicit in that is that you also have to be able to get rid of the derivative in here. How do you do that? Well, calculate the derivative here. dv dt is the derivative of this, 1 minus n y to the minus n times dy dt by the chain rule for this, right? So their dv dt gets replaced by the derivative with respect to t is dv dy, this part, times dy dt. And so in order to make that effective, what I'll do is I'll multiply through the equation by 1 minus n y to the minus n in here, and that'll make this dv dt. Now, let's just see a quick example. If I multiply, well, actually, let's not do the proof, but this will convert a Bernoulli equation into a linear equation, and the proof is just that this is a special case of the method we just did, actually. I'm running short of my video before it runs out, so I've got to finish an example here. Here's an example. dy dt plus ty equals 3ty cubed. Oh, if only that y cubed wasn't there. It'd be a linear equation, I could solve it. Well, it's still a Bernoulli equation. I'll make the substitution, v equals y to the 1 minus 3, this exponent here, or y to the minus 2. If I make that substitution for v is y to the minus 2, I have to get dv dt to replace dy dt, so I calculate dv dt as the derivative of y to the minus 2 with respect to t is minus 2y to the minus 3 times dy dt by the chain rule, right? I'm taking derivative with respect to t, not y. All right. So I need to substitute out to get dv dt minus 2y cubed dy dt. So I multiply through by minus 2y cubed. That's what I was indicating up there. You multiply through by what you need to get dv dt. I'll multiply through by minus 2y cubed the whole equation and get this. So this equation times minus 2y cubed is this equation. And now this will be dv dt because I did that. I got dv dt here. Y to the minus 3 is v. Let's say, y to the minus 3 times y to the minus 2 is v. So this is 2t. These things make v. And minus 6, y to the minus 3 and y to the 3 cancel, and you get t. how could I get so lucky on both those things? I must be having a cooked problem, right? No, actually, every time you have a Bernoulli equation, this always happens. This always becomes a function of t times v. These things in y always turn into v. And these things over here, the y's always cancel. So we didn't just get lucky. Every Bernoulli equation this happens. You get dv dt plus a function of t times v equals a function of t. It always works and you get lucky. Isn't that nice? I wish life were like that, right? This is linear. It's what always happens. It converts into a linear equation. In standard form, right? dv dt plus p of tv equals f of t. Standard form. So you take mu equal e to the minus 2t dt is e to the minus t squared. And you write the standard solution form 1 over mu, integral mu f of t dt. And you get this, 3 plus an arbitrary constant times c e to the t squared. There's a Bernoulli equation. These are a lot. Again, just practice these and I think they'll start to come out. But you just want to be able to recognize, oh, this one's homogeneous, right? Maybe it's a quotient of linear expressions in T and V. This is a special case. Oh, this looks like a Bernoulli equation. So it's like calculus where you did integration. You look and say, oh, that kind I recognize. This falls to integration by parts. Oh, that one I recognize falls to a trig substitution, right? Same thing here. You just want to get used to recognizing it's this kind of equation. I use this method. After all, solving differential equations like this generally amounts to integration eventually. It's got the same drawbacks as integration. You have to memorize the different methods. It's a bunch of cookbooks. They're not a single recipe fits all.